All right, so today we're going to be talking about cellular respiration and fermentation. The overall goal of today, thing you guys have to keep super focused. That's the purpose of today is let's get energy out of food, right? So there's going to be two types of energy we're going to talk about. So in my notes, I tried making those pop out as much as I can. And the things that I want you guys to keep an eye on, right? One of the energies we're going to super follow is basically electrons, right? Or having having a lot of extra electrons, bringing that negativity. So we're going to carry that with NADH, and one time we're going to do it with FADH. I'm sorry, that I should write it like this. I think it's NAD plus, right? Which eventually grab hydrogen, they also grab electrons and become NADH and FADH. Right? So this is one way to capture energy. They're going to basically hold electrons for us. The part of what we do with those electrons, I'm going to bring it up more next week. But keep an eye on this. The other thing that I want you to make sure you're constantly keeping an eye on where they're moving and what's going on with them is the creation of ATP. That's the other big molecule. This is one of my favorites. We use it for so many different things, right? ATP, remember that's an example with me and Hank, where we're kind of bumping into each other because there's so much negativity. They're pushing, repelling each other. That means that it's this super unstable thing. It gives the phosphates and it'll power up other reactions, right? This one, I want you guys to, it's gonna come in two different ways, right? One way that we can create it, it's gonna be substrate level. And then the other way we can do it, it's going to be oxidative. So today's presentation, I'll be talking about, I'm going to focus a lot more on this one today, like the substrate level, which literally means there's an enzyme that grabs ADP, something that has a phosphate to it, and literally smash them together, right? At substrate level, oxidative, we only use the charge from up here, and we use it in the cross-trans membrane to get the energy out of it. This is going to be next week. This is the one we're doing something. Yeah. So I'm gonna draw a bunch of stuff today. It's a big story for you guys. I'm hoping that this will be the thing that you guys are like, hey, I saw the NADH come out, I saw the ATP come out, we're seeing the energy. I am trying to not be super heavy on the enzyme names. I'll try, I promise, but I do love them and I get excited. I'm gonna bring them up, but hopefully for the midterm, I'm not gonna go crazy with it. like I said before, remember, purple slide, that's my favorite slide. That's the one when it comes to the big summary. This is the one that I want you guys to focus on. So slide 26. Here, again, if you do as just super emphasis, let's ignore the stuff in the middle, right? As always, as we're going through this process from sugar, what I want you guys to keep an eye on that's coming out is we have NADHs coming out, right? One energy molecule. The other thing we see coming out is going to be ATPs. We get to the next step, we have NADHs coming out. And we have, in this case, we don't have ATP yet. And the final one, you see NADHs, FADH, and you have ATP coming out. So those are the products coming out, right? That's the overall story. As I'm going to go through the story today, I'm going to be talking about how basically this is a 6-carbon ring. And we're going to show you how at each step we're going from 6 carbons to 2 sets of 3 carbons. Then we take off 1 carbon and leave it as a 2 carbon. And eventually we break off the last 2 pieces of carbon. And we're going to talk about the energy. But the big overall story of today is let's get ATPs, let's get NADHs out. And these are the 4 processes. Oh, sorry. The 3 processes I'm going to bring up today, right? Glycolysis, the pyruvate processing, and the citric acid cycle. The electron transport and oxidative stuff, that's going to be next week. Yeah. All right. Now that I give you my overall, that's the goal we're going to get out of today. I'm going to have to give you guys some background. Hopefully I don't lose you there, and then we're going to bring it back to the story. All right. So we've talked about this before. So upstream, before this process even starts, remember our energy is all coming from the sun. Photosynthesis allows the plants to transfer that energy from like light energy. They can basically glue CO2 together with water and use the energy from the sunlight. That powers the reaction of making ourselves, they're called hydrocarbons, right? Carbons with hydrogen groups on. What we're going to talk about today, it's going to be our glucose. Then what we're going to get into is about how do we break that glucose down to get the energy out of it, right? I think they were saying like, I think it's glucose is the one that they make rockets. They put sugar, I think it's phosphorus. And basically, you can make the rockets that go into space. Crazy amount of energy released all at once. Today, what you're going to notice is as we go through these steps and talk about these molecules, we're going to take out energy and engage ATPs progressively, and we're slowly going to bring the energy of the reaction down over time. So for this part, there's going to be 2 ways that we can break down this energy. One of them is going to be cellular respiration. And in this case, it's when we're bringing out the energy, we do require oxygen to be present. Right? That's kind of the thing that we do in our systems. The other way you can do it is through fermentation. And this happens when oxygen is not present. Later, I'm going to draw my little map about how this is receiving. I'm going to show that fermentation in a different color just to show you where it kind of breaks off into a tangent, but it's not going to be that big for us today. I'm going to focus a lot on the fermentation process itself. And let's keep going. Okay. And this concept, I want you guys to be very familiar with redox reactions. So for this part, I'm going to draw this. All right. All right, so for this reactions, we're going to be basically talking about how electrons get transferred, right? But the goal is to see how charge gets transferred. In some cases, you actually transfer the electron over, which is like through making and breaking covalent bonds. In other cases, you can do it by just playing with a different molecule that has different electronegativity. So technically, you'll still be sharing the same amount of electrons. It'll be, you just have a breathing partner in that molecule. So for this one, you can see. Here, we're going to talk about oxidation, and we have our reduction, right? Oxidation means loss of electron, right? And then for reduction, you're gaining an electron. So that means at the end of the day, when you gain an electron, you become negatively charged. When you lose an electron, you become positively charged, right? Effect. As we go through today, we're actually going to be keeping track of events like this that are happening, of oxidation, and then reduction occurring from sugar. It's going to basically get oxidized. And as it's getting oxidized, we're actually releasing energy from that molecule. All right, so like I said before, one way that you can lose your electrons was like this. Right, where it's you guys want to call we have salts, which is sodium chloride. Here we're looking at this molecule, no charge, it has an electron, right? This electron can be transferred over, like when you put it in water, to dissolve. Now you have two different ions, right? You have your Na with a positive charge. Because it lost an electron, we call it oxidized, right? That's oxidized now. Opposite to that one, since this gained an electron, now this one's now considered it got reduced, right? At the same time, you can call, so this oxidized, technically, you could call that a reducing agent. Because with its bond, or its ability to give an electron off, it reduces this guy. Right? So reducing agent means that it can modify the other one. This is called an oxidizing agent because it can oxidize soda. Does that make sense? All right, cool. Now for the next part, we're going to be talking about another way to do this charge transfer or electron transfer, but it's not through a difference in the amount of electrons you have, just how they're shared. So in this case, I want you guys to think about this a little bit like there's the electrons when you have something like between carbon and hydrogen. Remember these are the non-polar stuff we talked about before, and we said they share the electron equally. When they do this, the electron is kind of the furthest away from the center of the atom, from the nucleus, right? As it's spinning, the further away you're from that center, the more energy it has, right? So that means that when you find your electrons are being shared between them evenly, this particle or this covalent bond technically is sitting somewhere where it's like it has the highest amount of energy, right? So CH bonds, high amount of energy, even our O2, because their electronegativity is similar, right? They're sharing the electrons out there. Technically, those electrons have a lot of energy inside of them. As you combine partners where one is more electronegative than the other one, and you pull the electron towards it, that means that these basically have less potential energy. So here you kind of see a little drawing of CO2, the oxygens are putting those oxygen bonds. In a water molecule, the water is putting those bonds. So those are basically lower energy, more stable. These, we're going to kind of go through them today. This, we're going to be looking at the reaction of burning hydrocarbons, burning sugar. In this case, again, we're looking at the spacing, right? Carbon, hydrogen, you can see the electrons are right in between those. So there's a high energy particle. Our O2, again, the electrons are in the middle. We have that energy basically stored up. As we go into today's reactions, what we're going to see is that the products that we're going to make from our sugar and oxygen is going to be our carbon dioxide and our water, right? Should be there. Okay. So what we're making today is going to be CO2, and your H2O is your product. Now you can see the electrons are basically shifted to the edges. And as we've been talking about last week, we have our reactants, right? Your CHs, your O2s, high energy. We're producing CO2 and water, which are low energy. So that means that when we're doing this, our delta G is going to be positive or negative. Our energy coming out. This minus this.
It's negative.
Negative, right? If it's negative, it does means negative means energy is coming out. This reaction is exothermic, right? That's the whole point of it, right? We have sugar, we're going to burn it off with O2, and we're going to produce energy out of it. And this is where we're gonna get it from here. And literally the energy is coming about how spaced out those electrons are between the molecules. That makes sense? Everybody's good? All right. So charging electrons. So that's good. All right, so here I'm kind of going even more into detail, kind of explaining it, right? Make sure I'm really emphasizing it that you see this bond before the electrons were in high energy state split between the two. And then down here we see that they're getting oxidized in the sense that that oxygen is now technically has more electrons because they're sitting closer to it. Right, so you've oxidized this. It means that if this has been oxidized, that means your carbon has been oxidized because it's lost electrons. And then your oxygen has been reduced because technically you gained electrons because you spend more time around it. So it's not bigger than HCl, but it is happening, and that's where we're going to get that power from. So again, so this is kind of summarizing the whole thing that it's like the goal here is we're going to oxidize sugar, and from that oxidation is where we're actually going to put out the energy based on which bonds. So in this case, we're going to see a lot of storage and energy. Here are your CH bonds. We normally call them hydrocarbons. For us, it's sugar. For your car, it's your gas, or like methane, propane, all those. CH, that's what we're hydrocarbons. All right. So that's one way to, that's how we're putting out the, how we're changing the electrons. Now we're going to talk a little bit about how we carry, there's also another way where we can actually carry the electrons when we put them out. This NAD is what I'm talking about up here. Right. If we zoomed into this process and see how it actually works, is when we're making it, you're actually bringing in electrons. You're also bringing in the hydrogen molecule, right? So we're getting modifying this NAD. It gains the electrons against the NH. We then are able to basically carry it. Then we can shift those to an oxygen. When we give it to us oxygen, we're going to that's what we're going to be producing our it's our CO2, where it's going to be used to power up, releasing of the ATPs. But they're basically carrying it. Those are reusable. Once you get NAD, once you get rid of the hydrogen electron, you can reuse it. You just kind of use it as a cyclic way of stripping electrons from the reaction itself. All right. This is a good map of how this reaction is actually happening in the cell. So I think maybe this one also should be purple. Yeah, purple slide. So our first step is going to be glycolysis. Right, so now I'm going to get into the process itself. All right. So we're going to start with glycolysis. It's going to be our first process. This is happening in the cytosol. In this case, let's keep track of the molecules, right? Here we're going to start with glucose. In my drawing, I got a little bit lazy. I didn't put the hydrogens and oxygens and stuff. I only kept track of the carbons. So we're going to start with glucose, which is going to be 6 carbons. So it should be a little shape like this. So in this step, for glycolysis, when we're making it, we initially invest energy into this. And okay. So we start with glycolysis, glucose, 6 carbons. At the end of this process, we're going to end up with your, we're going for this one to make pyruvate. So you're going to start with this. The goal of what you're going to produce is going to look like this. Carbon, carbon, carbon. Carbon. So you're going to go from having one chain of 6 carbons to you're going to end up making two 3-carbon chains. At the same time, you're actually gonna invest ATP to power this reaction up. So you're gonna put in 2 ATP, you're gonna get out 4, but the net effect of what's coming out is gonna be, so down here I'm gonna write the net. The net production here is gonna be at this step. At the end of this step, you're also gonna produce 2 ATP. Yeah. So that should be what we have up there in the drawing. This pyruvate then can get transported into the mitochondria. We're gonna have the next step happen, which is gonna be your pyruvate processing. So this guy, we're gonna go from this 3-carbon, and we're gonna end up producing, this is processing. Here we're gonna produce acetyl-CoA. And here it's gonna be basically, you're gonna produce a 2-carbon chain. And it's gonna be attached to your CoA. Right. So 2 carbons. And for this step, we're gonna produce, again, I think this is let me make sure I got it right. Yeah. Yeah, no, here we'll just produce, we're gonna reduce the CO2, but I'll bring that in the drawing later. Let's go back up. All right, so the pyruvate processing kind of happens about right here. Then we're gonna enter into the citric acid cycle. Here it's kind of giving us the whole thing about cellular respiration together, but I'm gonna go into more details for the next step, which is this guy, right? So this kind of looks a little bit like how I'm doing it here. We have glycolysis on the outside with our glucose. So that'll be this. We're gonna produce a pyruvate, which is our 3-carbon molecules. This is gonna get transported into the inside of the mitochondria, which will be your matrix. So it'll be, remember here we have 1 phospholipid bilayer. Here's your second phospholipid bilayer. On the inside of that, that's your matrix. When we get it all the way into that, on the inside of the matrix, there's where we're gonna have the citric acid cycle happen. So 1, 2, oh God, I need more space, guys. So I do it over here. All right, sorry guys, it's gonna look a little bit. 3. It's going to be our citric acid. Cycle. At this point, we're going to be using this 2-carbon chain. We're going to keep processing it. And the goal out here is we're going to be able to produce 2 more ATP. We're going to use up the last 2 and we're actually going to make CO2, right? But again, we're going to be focused on this step down here. The final step is making, like I said, your oxidative phosphorylation. Which is going to produce that last set of 26 to 28 ATP. So this is the big overall thing that we're going to achieve. This we're not going to go over today. We're just going to stick on that front end. All right. So for this part, if we go back, you can see that at glycolysis, we're bringing out 2 ATP net. We're bringing out 2 more ATP in the citric acid cycle. And we're going to bring out 26 to 28 on this last step over here. Let's go back all the way to the beginning. And I want to keep track of the other molecule, which is our NADH, right? In this step, once we're done with this, we're actually going to bring out, at the end of it, 2 NADHs right there. At the end of pyruvate processing, here again, we're going to bring out 2 NADHs. And then when we get all the way here to the end of the citric acid cycle, we're gonna bring out 2 FADHs and 6 NADHs. All right. So that's the energy we're gonna be pulling out from the system as a big story as a whole. For this, I do want you guys to feel comfortable with this table. All right, so for this step, glycolysis, I want you guys to know that the molecule that's coming in, for example, here is glucose, right, your 6-carbon ring, that's coming in. Then what's gonna come out of this is you're gonna bring out these 2 pyruvates, which are your 3 carbon chains, and you're gonna bring out these 2 energy molecules, right? For the next step, when we get to the pyruvate processing, you're gonna start out, again, 2 3 carbon chains. From that, you're gonna produce this 2 carbon molecule, your acetyl-CoA, and here you're gonna be producing your NADH. Yeah. And for your citric acid cycle, here you're gonna start off with your 2 carbon chain, and you're gonna produce a little bit more ATP, your FADH and your NADH, and you're gonna actually produce a lot of CO2. So I'll do that on my 3rd round through this thing. All right. So this one, I kind of want you guys on your own to fill this in more detail. I don't think this is enough space. So make sure for each step you write what's coming in and what's going out. And also, if you guys clean this up as practice, make sure you're writing down what numbers you're getting out of these guys. All right. So let's do this. So we're gonna now zoom in to this first step, and we're gonna see how do we actually make energy out of that first 6 carbon chain, you know? So here we're starting with glucose. There's our 6 carbons. We're first gonna bring in ATP, and we're gonna transfer a phosphate group to both ends, like this, right? Phosphate in the front, phosphate in the back. You guys remember last week we were talking about how to glue the sugar molecules together? If they have low energy, by bringing in this phosphate, you can basically make them higher energy molecules. And that's kind of what we're doing, temporarily bumping it up with energy. We then are gonna go, we're gonna cut this molecule in half. And once we cut it in half, we're gonna use a different protein. We're using different proteins to kind of pull out the electron, and we're gonna pull out the ATP from it. So this 3 carbon chain with a phosphate group, once it's cut, we're gonna actually use this phosphate to help us power up the reaction of charging up an ATP. In this case, this is called the substrate level, right? And it means that the phosphate is attached to a different molecule, and you're actually gonna make an enzyme that's gonna hold this thing together, right? As a pocket for ADP, as a pocket for your 3 carbon sugar, and it can grab that phosphate and it can force it to transfer it, produce the ATP. Right? So we had already put 1 ATP in, and this is one way to take that same ATP out. So in this step, when I'm talking about the net production of 2, the real numbers are, we put in 2 ATPs to power up the reaction. Once we have this proceed forward, we can actually pull out 4 in total. All right, so for this one, here it's kind of showing you the same diagram, right? Here would be your 6 carbon chain, 6 carbons. The 2 phosphates, the 2 ATPs are used up, charged the ends. Right, you set it up something like this. Phosphate and your phosphate. Right? Temporarily, this is going to get split into those 3 carbon with the phosphate. We then bring that out using that substrate level. We can produce the 4 ATPs, because in one of the intermediate steps, we end up charging up so that it's right. When you cut this, you're going to produce two copies of the same thing like that. Right? Then from here, we can actually pull the energy from this molecule, that's the thing that we're using to basically move ADPs into ATPs from this. All right, so from there, at the same time, we're transferring, let's put that on here. So in this case, right, I want you guys to kind of look at this one up here. We have, this is our 3-carbon chain, kind of like my little drawing that I have up here. You have the phosphate attached to it. When we zoomed into this bottom carbon, here's going to be the top carbon. You see we have it HC double bond O, right? This, we're going to have the enzyme, this triose phosphate dehydrogenase. And what it's going to do is, it's going to remove the hydrogen from that bond, and it's going to take it with the electron, right? That's where you're donating this. And that's what it's going to basically bind it to that NADH. Remember, that's that molecule that temporarily holds it. As it's doing that, we actually bring in a phosphate group. The thing about this phosphate group is it's not coming from ATP where it's in the high energy state. It's just the phosphate group by itself. So technically it would be considered low energy. So when it's doing that reaction of releasing the electron this way, we use the charge of the phosphate group to basically glue itself into this 3-carbon chain. That kind of makes sense? So we're technically dropping down in energy, but we're bringing in a phosphate group that's going to be now charged up. So this little chain of 3 carbons and phosphate becomes a 3-carbon chain that now has 2 phosphates, right? This one came from ATP to power the reaction. This one, we made it from like inorganic phosphate, something just floating around in the solution. So it wasn't high energy, we just made it into high energy. At the same time, we also we're saving up, we're investing in some of these NADHs. That makes sense? So this step is one of my favorites. Make sure you guys feel comfortable with this step. Any questions on that step? No? All right. So you guys do see that we kind of lose that hydrogen basically leaves with that one. The oxygen group is coming from this phosphate to set this little bond up. Yeah. At the next 2 steps is going to be, we have those phosphoglycokinases, and that's where we're having this thing happen, right? They're transferring their phosphates into ADP to ATP. And since we have a molecule that has phosphates on 2 ends, and we have 2 of those, we can make a total of 4 ATPs. So initially we invested 2. Through this, we can pull out 4. So we have this, and this gets us to the last step. The biggest thing is just feel comfortable with the pyruvate at the end. Right? So in the midterm, I want you to feel comfortable with this part of 6, with the phosphate gets modified. We make 2 of this 3-carbon with phosphate. We eventually make this phase, 2 phosphates at each end, and then we can pull out 4 ATP total. Yeah? All right. So at this point, we've just covered up this part, right? We started with glucose. This is your 6-carbon. We went through glycolysis. Key step, we pulled out Net2, and we pulled out 2 NADHs. In reality, we put in 2, and we pulled out 4. The next step is we're sitting right here, which is your product is the pyruvate, and we're going to go into the pyruvate processing, how we go from here to here. And for this one, the thing I want you guys to keep an eye out is we're hoping to pull out 2 NADHs, and we're going to be producing CO2. So this is the first time we're actually going to see that this molecule is going to start to get smaller, right? Or that we're actually starting to lose carbon. So for this, again, feel comfortable. We're starting out with just these, with your pyruvate. As we're going into the process, we're going to produce CO2, we're going to produce our NADH, and we're gonna produce this acetyl-CoA when we're done. As this is coming in, if we go back to talking about energy, right, and electrons, and about when they're carbon with hydrogen, technically that's your high energy state. If you added one single bond with oxygen, you're gonna get oxidized, right? You're gonna take away a little bit of the charge from it. You make a double bond, you're gonna take more charge from it. Here, this carbon all the way at the top, it's currently working with two oxygen groups. One's double bonded, the other one has, you can see it has a negative charge on it. It's gonna super try to steal the electrons from it. This means that at this point, it was higher energy than carbon, and now we're bringing it down to lower and lower energy levels. At this point, we take out the last little bit of energy from that carbon. This is where we drop off our first CO2, right? So back here, when we started with the first one, this were CH, C bonding with H, bonding with OH, high energy, right? As we're going through this process, we're basically making it get more and more oxygen passed to it. We're bringing the energy down progressively lower and lower. This case, when we reduce this, at the same time, for this one, we're gonna take out again, we're gonna take out, using one of those NADHs, and we're gonna be stealing the electrons from that reaction. We're gonna be using electrons and hydrogens. And we're gonna make this smaller molecule, which is gonna be this acetyl group. So you guys remember that one is C, a carbon with a double bond is an oxygen, right? We have our acetyl group right there. And this is gonna basically give you the form that we're gonna temporarily hold in. For this step, I don't think you guys to remember that drawings as much as I'm having on this one. So this will come from 3 to 2. The acetyl-CoA, just, so I'm not sure it's a serine, the coenzyme A, it looks like a really complicated ATP. Don't draw it at all, just give me CoA. That's CoA and I'll be fine for the drawings. Yeah, so I'm cool with this one. And again, in this step, no ATP, just NADH. All right, so now we're currently at this step. Now we're inside the matrix of the mitochondria. Now we're gonna get a little bit into the citric acid cycle. All right. So for this one, we're on this side of the floor now. For the citric acid cycle, we're coming in with our 2 carbons, and they're currently holding on to that, the CoA, right? At this point, this cycle, if you go into it, it gets super complicated. They have a bunch of drawings. There's a this thing called oxaloacetate. It's OXALOACETAE. So it's a 4-carbon chain. And you basically temporarily bind these 2 carbons to that 4-carbon chain. So you end up producing this 6-carbon chain temporarily. As it's going through this, you're going to end up first producing this NADH. You're going to make 3 NADHs out of it per every 3 NADHs per every acetyl-CoA. So be careful with the math, because here we're imagining only one of them going through the cycle, it produces 3, but since in the step before, we actually still have 2 of these, right? These pyruvate make 2 of these molecules. We actually produce a total of 6. So we have 2 of these guys, right? So that's where we can produce the total of the 6 NADHs. Again, we can produce 2 of those FDH total, and we can produce 2 ATP. This just represents one single cycle through it. Let me open up a drawing of it. This is where I was having a little bit of extra trouble, because I normally enjoy watching the molecules get modified. So when I was making, trying to make my notes yesterday, I was about to draw this out, but then I realized that if I go into it with you guys, I might confuse you more than I need to. I want to show it to you just so I know it is there, and if you ever get to see it, you can glance on it. But I don't expect you to know from the picture, you know. So here we have that acetyl group coming in. Again, we're gonna be focused on these two carbons, right? These are the ones that are coming from our original glucose. So this is that oxalate that I was talking about. Sorry, it should be this one's already merged in, but it should be a 4-carbon chain. You basically produce this larger molecule, and what it's doing is, here's the first event, where we're basically stealing hydrogen. We're going to steal two electrons, 2 hydrogens to take the charge out of it when you're making the bonds. Again, NADH, that's the first time we're going to put out energy. As you go to the next step, you're going to see that we're going to do it one more time, where we're putting out a CO2 molecule, something that we've completely oxidized. So we're taking out all the energy out of that molecule, and we use that to power up creating those NADHs, okay? Storing, investing more into those NADH molecules. Then, where is it? Here, we use, we can actually, that's where we pull, we do one of these changes, the substrate level changes. We use that molecule, it gets phosphorylated, and we use that to refold to produce those, what's it called? We're producing GTP. So we're powering the reaction by folding a phosphorylated molecule, transfer it to a ADP to an ATP, right? As you kind of go through it, it's basically releasing carbons as carbon dioxide. At the same time, it's using the energy of being oxidized to produce those NADHs. That's the main thing behind it. So going back to this, that's why when they summarize it, the main thing that they care about is CO2s are coming out, and you're making that oxidation process, so it's helping you produce those NADs into NADHs. You guys feel comfortable with that part? Yeah. So feel comfortable with these numbers down here, and talk about that the energy is all coming from the from the carbons being oxidized. So again, I want you guys to fill this one up with the numbers. Tell me the whole story. At each step, draw what comes in and what comes out. And then you guys have been doing pretty good at looking at those tables with the products and reactants, right? Where like how the energy is exothermic, and you can bring power out of it. Last time I showed you those 2 types where I was like, hey, you can have an endothermic, exothermic power endothermic, right? And it's like, as long as you're a high molecule, you can kind of bring it down. And then here's the long story of putting glycolysis together and kind of looking at the same table of what's happening with that energy, right? So when we start off, here's your glucose, right? You have your 6 carbons, you have this high energy molecule, and the potential is coming from the fact that it has carbon-hydrogen bonds, right? That's your high energy. As we're going through it, we first start off, we're powering up the reaction. Remember over here, when we first force this ATP, we use ATPs to power this phosphate and this phosphate. Now we have a higher energy molecule. So you can see the energy of this actually goes up, right? After that, we're going to be talking about what we do when we bring out the energy. That molecule is phosphorylated. It looks like this. That's the highest energy it's going to have. It created that extra energy by bringing in that free phosphate group. Now you're going to use that to oxidize a little bit of itself. And you're going to release hydrogens and you're going to release electrons. And that's when you have this big drop in energy, right? So that takes you down and you release some of that energy. After that, you then use that substrate level binding and you give away your ATPs, right? They're your ATPs. You see the reaction getting smaller and smaller. Then we enter into this pyruvate. You can see there we still have a pretty good amount of energy. And there again we use, we're going to be losing from this one to this. We're going to release a burnt out or oxidized carbon. So we're going to lose one from the chain. We're also going to be using that energy that's being released from this oxidation to power up that NADH reaction. So again, we're going to bring it down a little bit lower. Then the next step is once we enter the citric acid cycle, we have that 6-carbon chain that we're going to basically burn off 2 of those last carbons left behind from the original glucose. As we're burning them off, we're going to be storing those electrons and that hydrogen inside those NADHs. We're also going to be producing these FADHs. And of course, we get a little bit of a burn from the ATP, burning energy. So sugar molecule, super high energy, and you're slowly going to release this energy into ATPs, right? At the substrate level, you're also going to release it as electrons and hydrogens using these NADHs and FADHs. That make sense? Overall story? All right. I'll give you this one for the card. If you wanna answer that one, you can answer that one. If not, put a good question on the cards for me. And I think, next week we have an in-class assignment, right, for Wednesday? And also we have homework today. So, the cool thing is, I'm gonna try making the questions for the in-class assignment similar to the way I'm gonna write questions for the final. So then on that Wednesday, I think we're gonna do, well, let me ask you, how do you guys feel about that, presentation style in-class assignment? If you want, if you guys write it on the card, that way you guys feel comfortable, write it on the card. This week you can make them anonymous, don't put your name on them. Do you like better when the person presents and shares it with the group? Or do you like it better when you guys are kind of in groups doing your own work and I walk around? And then I'm really hoping that for that Wednesday class, give me some feedback on the questions for this process, right? I love to go into super detail, and that's one of my big caveats that I like. If I can see the molecules, I understand it. If I drew the overall stuff, I feel like I don't get it that well. If you guys need me to go more into detail, bring the writer into detail, do more pictures, let me know. But so feel free on that Wednesday thing to give me a little extra beats or send me like an email or something. Yeah. But we'll see. Oh, sorry. So should we do on your card right now, right? Should we do presentation or should we do individual groups? And if you're not in class, email me.